Hi students, welcome back to computer vision video lectures. In the last class we have seen we had a brief introduction to optical flow. In this we would quickly recap that whatever we have seen in the required things for this class, and then we would go with how smoothness constraints are also incorporated into the optical flow. Mainly we would be discussing about two specific methods: optical flow method proposed by Horn and Schunk, and then Lukas and Kanade optical flow method. These would be what we would be discussing in this video lecture. Okay, yeah, we will switch on in this from sometimes from the PowerPoint mode to notebook mode wherever some derivations are required. Okay, let's go ahead. This is what we did in the last class, where we ended up is if you simply impose the brightness constancy constraint and try to find out a mapping of a given point at time frame t to the next time frame t plus 1 based on the constraint that it should have the pixel should have the same intensity there, and you let the pixel move around to find out an intensity value that's same as the intensity of pixel xy in time frame t. We ended up with this equation where dou ix by dou x into u plus dou I by dou x into u plus dou I by dou y into v plus dou I by dou t equal to 0. Okay, here we have seen this again. We have seen that at a given point all that this minute, let me make it mute. Okay, yeah, so what we get because of this inner product and gradient of i's inner product with uv is that you will be getting a component which is in parallel to the gradient. In other words, you would be getting just the component through which you could know for sure what is the component that is perpendicular to the edge, but there could be multiple possible solutions with varying components that are parallel to the edge. Again, we will come back to it a little later while we are discussing about the Lukas and Kanade method, but this is what we have discussed. Say for example, in this diagram, uv and u plus u dash plus v plus u dash, both of them have same component. The parallel component is same in parallel to the gradient, or in other words perpendicular to the edge. They are having the same, but essentially they would result in, they are all valid solutions to it. Okay, so we had essentially one equation, right? The equation we have seen in the previous slides. And how many variables are there? Two variables are there. You need to find out at a given pixel its movement in the x direction as well as its movement in the y direction. So there are two variables here. So to deal with this, usually more constraints are imposed on it, and particularly the smoothness constraint. So let's start with the Horn and Schunk method. So to do this, let me switch to the notebook mode. So I'll share my screen here. I'll move to the notebook here. Okay, so hope this is clear. Yeah, so what we would see now is the method smoothness constraint in Horn and Schunk method is what we are going to see now. Proposed by Horn and Schunk, okay, from Artificial Intelligence Lab in MIT somewhere in 1980s. This has been proposed. Okay, so the energy term which we got earlier from brightness constancy constraint, let me write that out first. So what we do there, that you could pose it as an energy minimization problem where you go through all pixels, okay, and at each pixel you do ix into u plus iy into v, the subtraction of it from dou I by dou t. This is what you would like to minimize at each pixel. Okay, sum of that for the entire things. Again, ideally this should be 0, but it could have small values, so to deal with the negative values, this is how you could write as an energy formulation for the brightness constancy constraint. This is what we have seen in the last class. Now in this class what we would do is, what Hans and Schunk method does is it imposes a smoothness constraint on top of it. So it imposes a smoothness constraint. So it assumes, let me first write how does that constraint will look like, and then we will take a discussion about that. Let's call that smoothness constraint with E subscript S. You again go through all pixels, okay, and what you are going to minimize here is ux square plus uy square plus vx square plus vy square. This is the smoothness constraint that has been posed here. Take a closer look at this. What it essentially means is, what is ux? So you are so the ideal for this value to be, when this function would be 0, before that, to make sure you have got what each of those variables means correct, you got it correctly. Let's write what it is, what it means by saying ux. Let's say at a point xy, how can we write that value? Let's say ux at a location x and y. What does that mean? U is the displacement in the x direction at the location x comma y. That's what is u of x comma y. Subscript x is derivative of these u values in the x direction. So how could you write? Assume you are taking forward derivatives, then this would be equivalent to x plus 1 y minus u of x comma y. With that, now suppose you want to see how this displacement in x, the derivative of it in y, that's what you would like to take a look at and minimize that. So how would you do that? Then this is uy, okay, that would be equivalent to uy of x comma y. That means u of, again assuming you take a forward derivative, this would be equal to y plus 1 minus u of x y. Now you already know now that vx of x comma y would be equal to v of x plus 1y minus v of x comma y. Similarly, v of x comma y is equal to v of x comma y plus 1 minus v of x comma y. So here v of x comma y plus 1. Yeah, pay attention here, otherwise this could be slightly confusing. What is it that you would be getting at the end of your optical flow? You would be obtaining the values of u and v at every pixel. Okay, so let me just at every pixel these are the values you are getting. What is this minimizing es? What does that mean now? That the derivatives of u and v, each of them in both x and y directions, should be minimal. That means if at a pixel at location x has let's say u0 value, a next horizontal neighbor also having the same value would make ux to be 0, right? Similarly, if it has a value of u0, a pixel at x0 has a x0 comma y0 has a u0, so this uy becoming 0 means the pixel above it is also having the same value of u. This would ensure that a neighboring left side or right side pixel has the same vertical displacement as the current pixel, and this ensures that a pixel which is above it has same vertical displacement as the current pixel. So this is, you could already notice that this is a global smoothness constraint. This is a global smoothness constraint. Okay, when this would be equal to 0, of course when the whole image moves by same value in u and same value in y, then this would have a 0 value. Well, you can't get one of them, you will not be imposing any of them to be equal to 0, but you take now you formulate it as an energy minimization problem where you have both these terms. Let's say EC plus lambda into ES. This is what you will try to minimize. Okay, you minimize it and compute minimize and compute the values of U and V at every pixel. And this is the weighting factor. So that this is the weighting factor between these two terms that will tell you whether the smoothness has to be given more weight or whether the brightness constancy constraint has to be given more weight. This is the Hahn and Schunk optical flow method. Okay, hope this, yeah, this is the key. These are EC and yeah, so this is the term EC, you have it here, and this is the ES. What you try to minimize is this E equal to EC plus lambda into ES. Okay, hope Hahn and Schunk method is clear to you. Let me go back to the presentation part now. Yeah. Right. So that's you could see here. One thing should be clear, that it assumes that if the whole image has same displacement in the x direction and as well as same displacement in y direction, the smoothness term would be 0. That's where when you give a high priority for the smoothness term. On the other hand, you have a constraint on the brightness which would try to find out in its neighborhood which is having the best match. If you give that's something by playing with lambda, on whichever term you have more confidence, accordingly you will play with the value of the weighting factor lambda there. So the next improvised version of it is too harsh to, or a too strict constraint to assume that the whole thing should move in the should have the same displacements in x and y. For example, as you consider a case where you are tracking vehicles, where you have a camera fixed and the vehicles are moving from one frame to the other frame. You want to record how much it has moved, so that maybe you want to measure a velocity of it, or you want to keep tracking of it, or whatever be the application. Assume that you want to do certain things, such things. So then, assuming that your whole image moves by the same displacement in x and y is a too strong constraint to impose. And another more practical and more widely used is the Lukas and Kanade flow, where you would I would say pretend, then meaning would become clear as we try to understand it in more detail. So here what you pretend is, rather than the whole image having the same value of displacements in x and y directions, the pixels, all the neighboring pixels around that pixel, all of them together, put together, have the same displacements in x and y. That's what this Lukas and Kanade flow assumes. Okay, so let's go through it in bit more detail here. So for that, again, let's work it out on the notebook. So let me move to the notebook mode again. Give me a minute. Okay, just a minute. Yeah, let me go to this notebook again. Now what we would be looking at is Lukas and Kanade method. Now assume that for a given pixel you consider around that a 5 by 5 window. Okay, that's again for an example I am considering a 5 by 5. It could be any value depending on that. Now the assumption is that all pixels you pretend, okay, again let's pretend that we understand what we mean by pretend here. We will come back to it a little later. So you pretend that all 25 pixels have same U and V values. Okay, now so you now apply the optical flow this brightness constancy constraint at all these 25 pixels. Okay, so then what was the basically the brightness constancy constraint equation is Ix into U plus Iy into V is equal to minus IT. That was the equation. Now let's apply it at all 25 pixels, because for all of them they are all having equal displacements in x and y, right? So they all should satisfy this equation then. So let's write that out now. So u and v, once you find them, it should be same for all those pixels. So let's write it in a matrix form. Okay, so let me, for point p1, to identify it, distinguish each point, let me write it as ix value at p1, iy value at p1. Okay, this when you multiply it with u and v, okay, that should have, let me take this minus sign out because it's everywhere there for all those terms. So let me put minus here, and it of p1. Similarly, for the second point, it's ix of p2, iy computed at pixel p2, then I should be getting here it of p2. To do it for all the points, let's say for the last 25th point, p25 ix, iy p25, uv should give it of p25. Well, in the beginning we had one equation, two unknowns. What happened now? We have 25 equations and two unknowns. Okay, the other side of the problem we are now in. So this is, for example, for 5 by 5 size, this is 25 cross 2. Okay, this is 2 cross 1, and this is 25 cross 1, right? So you have only two variables, less unknowns, more equations. So how do you solve this? Again, this is solving a least square problem. How did we solve it? We did this similar thing in the transform analysis part. We have seen already how to solve this thing. So you call this, for example, as matrix A, vector D, vector B. Okay, now what would you do here? Hope you remember that. What you have here is AD equals to B. You multiply both sides with A transpose, that would give you A transpose A times D is equal to A transpose B. Okay, it's D that you want to find out. And by the way, A transpose A would be of size, A transpose is of size 2 by 25, and A is 25 by 2, so this would be 2 by 2. Okay, this is a square matrix. And then well, for that you need to find out an inverse. Okay, this is anyway 2 by 1. Okay, A transpose is 2 by 25, so this again 2 by 1. And then once you know it, you compute the inverse of it and move it to the other side. Okay, D equal to A transpose A inverse multiplied with A transpose B. So let's now write the expression for A transpose A. How does it look like? A transpose A, if I write the expression for it, A transpose will be 2 by 25. The first row would be Ix, all derivatives with respect to x would come here, Ix of P1, Ix of P2, and so on till Ix of P25. And here Iy of P1, Iy of P2, so on till Iy of P25. This gets multiplied with Ix of P1, Iy of P1, Ix of P2, Iy of P2, and so on till Ix of P25 and Iy of P25. Okay, so let's do the multiplication here and see what it results in. So basically that would be a 2 by 2 matrix here. So the first one would be equivalent to ix square of, so this first row and first column, so that would give you ix square of p1 plus ix square of p2 plus so on till ix square of p25. What about the second, the first row and second column? That would give you ix of p1 into iy of p1 plus ix of p2 into iy of p2 plus so on till ix of p25 into iy of p25, right? And in fact you get the same term here when you are multiplying the second row with the first column. So that's ix of p1 multiplied with iy of p1 plus ix of p2 multiplied with iy of p2, okay, and the last term would be ix of p25 multiplied with iy of p25. And the last one, the second row with the second column, would give you iy square of p1 plus iy square of p2 plus so on plus iy square of p25, right? This is your A transpose A, okay. Yeah, I could in fact write it in a summation form, the same thing, more concisely I could represent it, okay. So all I have here is ix square of pi, okay, and I is varying from 1 to 25 here, and this is ix of pi into iy of pi, and again this also I varying from 1 to 25. The same thing you have here, this is again varying ix of pi multiplied with iy of pi, and here again you vary iy square of pi. This is equivalent to the A transpose A. This is what the A transpose A is equivalent to. This is an important result. This is equivalent to A transpose A. So that's what you need to find out here. You take inverse of it, multiply with the A transpose B, would give you back the value of the U and V. Okay, with that, let's go back to the slides mode now. Right, yeah, here Lukas and Kanade, you got this out now. And well, this was again, that was somewhere in 80s it has been proposed, and this is 1981 Locus Kennedy flow has been proposed. Here you could see now whether this is solvable or not. In other words, whether that same question you could pose it as whether A transpose A is whether this A transpose A is invertible or not. How do we know that? So for that to know, what should have, so how could we say whether it is invertible or not? It's a 2 by 2 matrix, so you could tell it in terms of its eigenvalues, right? So when can you say that it's invertible? So both the eigenvalues should be large, right? Of course should, and then the ratio of those eigenvalues should not be too large, which means they should be more or less of similar magnitude. Okay, well, is it reminding you something, the same form? Again pay attention to what is A transpose A here. Okay, ix summation of ix square, summation of ix iy, summation of ix iy, summation of iy square. Yes, that's what you have seen it in Harris corner detector. The second order moments matrix which we have got there is exactly the same thing. So for this to exist, when this would exist and when it's a key point, we did some analysis there. So again, there also we have seen that for that point to be really a key point, we again made the analysis in terms of the eigenvalues. Lambda 1 and lambda 2 should be large and they should be of similar magnitude, right? That's what we studied there. So exactly now the same constraint holds good here. So this is when you would have it is invertible. So again, when was that the case? Suppose when was we were having that key points which you considered were reliable and detectable and then repeatable. For that to happen, we should have a texture in the given image, right? Or it should be the point you are looking at should be a corner point, or you should have a lot of texture, surrounding should be different. So that is only when this happens. On the contrary, if you have a, let's say, a very uniform region, your ix value and iy values will be 0, and then there is a problem with those eigenvalues. Even across an edge there is a problem. So exactly the same issue would come for a given point where its displacements are there, if you are pretending as if all of them have the same thing. So this, by the way, through this you will find out u and v for that given point. Now even for its neighbor, now you consider its own 5 by 5 region there. So that would eventually at the end of the day might give you to the neighbor, depending on your slided window, which are the new pixels, values of the pixels that have come, it could give you a different value there. Okay, so that's why initially we were saying we pretend as if they have the same value, because you do this calculation at every pixel, and by that process you will obtain the value for that particular pixel. Okay, so hope that is clear to you now, and you are able to connect it with also what we have seen with Harris corner detector. Whatever we have seen there holds good here also when it comes there. Suppose you are applying optical flow to a region which is having almost the same brightness. Okay, this is not going to work out. So maybe if you want, let me geometrically draw, also make an interpretation for this. Okay, let's again move to this mode. I'll go to the notebook here. Right, so earlier we have seen that suppose there is a strong edge somewhere. Okay, there is a, assume that there is an edge here. Okay, and your gradient of that is in this direction. This is your gradient of I at that pixel, right? And based on its value, there is somewhere your it, you could say that somewhere its minimum value is having, so that you are mentioning, you are doing a u and v. Yeah, u and v is inner product you are taking. So for example, this being your u1 v1. Okay, this inner product of that would give you the it value. And then this would give you a locus of points here. All these points, all these u and v values could have the same value. Suppose now you think that for this edge, so all you know for sure here is the component which is perpendicular to the edge, that is for sure you know, but the parallel component to the edge is not known. Now what would happen is, suppose if every point is doing in the same way in the set of all neighborhoods, there is a problem. But at another neighborhood point, assume that you have a slightly a different edge there. This is the edge for another neighborhood point. You have a different edge there. Okay, now we assume that this is its gradient direction there. Okay, and now that it for that is okay, you take the parallel to it. Okay, again these two didn't come parallel, but assume that this line you read right if you want. Okay, so then all these are all possible solutions now. So from that, if you have the textural differences around it, or in other words, if there is a gradient differences in the surrounding pixels, then you could get this unique solution around. This would give you a solution, this an intersection of both of these two things will give you the right solution. So if things are in place, even if there is another edge among them, that also should be somewhere intersecting you at the similar point. Let's say another edge also, if you consider, that should be okay. The locus of points for another edge should also be intersecting with this point. Assuming that there is another edge here, you could do the same thing. So that intersection is essentially, or minimizing the error with respect to the distance from all possible these combinations, is what you are essentially this is a geometrical interpretation of what you would get with Lukas and Kanade optical flow method. Okay, now let's take a quick look. Let's go back to our presentation mode. Okay, so yeah, so when you come back here, let's take a look at the errors that could encounter here, or the problems that you could face with Lukas and Kanade. One of them could be from one frame to the other frame. Okay, when you are moving, that might not give you the intensity values might not be retained for different possible reasons. So in that case, what you should be doing is you normalize the intensities in each time frame, and then you apply the brightness constancy constraint rather than applying it on the absolute values that were there in the images. Another thing, a point does not move like its neighbor. See, assume that there are people that are moving in an image, right? And maybe they will be moving in, so when you take a window, that window might having half part of one person and the other half of the different person. So you then imposing a constraint that all these pixels should have the same displacement in x and y is not an appropriate constraint there. So in those cases, what people would be doing is, if you could somehow do a motion segmentation, see the parts which are moving incoherently, and then on top of it you apply this, that's something people have attempted. Okay, another problem is when the motion is larger than a pixel. In that case, see, everywhere, if you recollect that brightness constancy constraint, whole idea is based on the Taylor series expansion, which assumes that the movement in x and y is minimal, so that is no more linear, and then in such cases people would be doing an iterative approach. Similarly, there is a problem with local minima. This optical flow could get struck with a local minima. This is an example that you are seeing here. As the movement is very small, then you would find out those black dot. Assume that in the first image, and the red dot, I'm talking about the left side image here. Okay, so that you could accurately find it out through a linear approximation there. But now the second figure here on the right hand side is showing you when there is a significant movement, and then assume that the color here is representing the same intensity value. Assume that, and now you could see that it would end up mapping to a wrong point on f2 of x, f1 of x, its corresponding point, you know there where it is, but here you would see that it is mapping to a wrong point here. That's because this is, again, it is referred to as an aliasing problem. Okay, and this is because the actual shift is too high, and but with that shift you now have some other points which appear to have a similar intensity values. Okay, so this is one example. Again, we are going back to the same example that we have seen with Harris corner detector. Okay, hope the similarities of this with Harris corner detector is also clear to you by this time. And now assume that you are moving your camera to capture these images, and what you are seeing in this GIF image is, once you move the camera, that's the next image. You see now there are some occlusions, particularly first image, the tree near that that house is occluded partly in one, and then there is there. Okay, there are other issues as well you could notice here. But so the point here is, you could, if it has moved too much, more some few tens of pixels, this won't be able to recover such high displacements. The conventional optical flow, even Lukas and Kanade, won't be able to do that. But here, what we are seeing, the same scene now at different resolutions. You subsample the image, But now you could observe here, when you sufficiently subsample that image, the which originally of many pixels movement, let's say 5 to 10 pixels movement, when done enough subsampling, can be of order of 1 or 2 pixels there, right? So what you do here to address this issue of large motions or large displacements is, you start with image 1, image 2. These are the ones which assume that there is 10 pixel movement when you have come from frame 1 and frame 2. Those are the image 1 and image 2. You subsample them. Now assume there, now suppose each pixel, there is a 10 pixel movement, would now when you subsample by a factor of 2 will become 5 pixel movement. You go again subsample by 2, 2.5 pixels. You go to the next level. So that's equivalent to 1.25 pixels. Then you apply your motion there, and then you map it to, you know, from that pyramid, you call this as pyramid, okay, this is how the way it is going on. You come to next finer level, so you move from the top of that pyramid to step by step to the bottom of the pyramid by appropriately applying this. So again, now that you have already know image transformation, image warping, this should be quite straightforward to you. So what you do now is you apply the Lukas and Kanade. I hope I could have here pen. No. Okay. The Lukas and Kanade method you would apply on the top of the pyramid at a very highly subsampled image where your displacement is of order of few pixels. Then you warp that image. Okay. So you already brought it to the closest thing possible. So by that, for example, assume that here it's 1.25 pixel. Assume that you got as 1 pixel there. Assume that. Okay, it has moved by 1 pixel there. So that means once you apply it, okay, and you come back to the next stage, there is only 0.5 pixels disparity there. So that level you do it 0.5 pixels. Okay, and this is how you iteratively would be applying this Lukas and Kanade method at multiple stages. So you go to the top of the pyramid with an image, highly subsampled image, downsampled image. You run Lukas and Kanade, you get the displacements, you warp these images, and then you upsample them, come to the next level, because then you have already compensated for large movements, and now movements are finer here. Then you keep doing it till you reach the bottom of the pyramid to the original image sizes. So this is what you would do in iterative Lukas and Kanade method. So these were the results from that the iterative Lukas and Kanade method itself. You would see here near the tree, if you directly apply, this gets screwed up obviously, okay, and then it clearly shows that the movement is nicely, so you move the camera mostly in this x direction mostly, so there you could see it nicely coming out when you use these image pyramids, okay. And then you iteratively update your displacements, and the final displacement would be of course the sum of all these displacements with appropriate scaling there, okay. So that's what iterative Lukas and Kanade method is, okay, right. So with that, what we have seen in this lecture is imposing smoothness constraints. We started with the Horn and Schunk method, where it imposes a global smoothness constraint, and after that we have come to assuming that all the pixels around the within the neighborhood of that pixel are having the same displacement, and from that that's like solving a minimization, this ax equal to b minimization problem, okay, least square fit in other words. And then it requires inverting A transpose B, that A transpose A, okay, that matrix is exactly what we got as the second order moments in the earlier one. So that's what we have seen, and further to have an inverse, there should be enough textural differences or enough intensity differences around that pixel, then only you could arrive at a good solution, to call it that way, okay. That's all for this lecture. We'll discuss probably in one more lecture few other methods for optical flow. Yeah, thanks for watching, and see you in the next video lecture.